In this lecture, let us discuss about the Rayleigh Pitot tube, and subsequently we will discuss about two methods by which we can perform drag measurement on cylindrical bodies and other two-dimensional geometries. This is the Rayleigh Pitot tube that we can see mounted on a side plate, and from your previous experience you can figure out that this side plate is mounted in the test section of a supersonic wind tunnel. We have talked about water based manometers or manometers containing lower density fluids, which are for subsonic wind tunnel purposes. When it comes to high speed applications, we prefer mercury over water because of the higher density, and so consequently the smaller pressure head displays on the manometer when we use mercury as the working fluid. So, in supersonic wind tunnels, when it comes to either single or gang type of manometers, it is essentially a mercury manometer that we are going to talk about, because we are talking about a very different much higher pressure range in the case of supersonic tunnel applications. So, we are talking about measurement of a change in pressure between 2 points. When it is a low speed tunnel, we go about using water, though density of water is much smaller than that of mercury, but that has an advantage because we then have conceivable differences in the heights of the manometric fluid in the limbs, and therefore, additionally by using inclined orientation of manometer etc., we can even measure small pressure changes. But in supersonic wind tunnels, most often we are going to talk about very high pressure changes, and they need to be recorded. And if we use low density fluids, then we will need enormously tall manometers, because the delta H will become very, very large. That is why choosing mercury is an advantage, because it has a specific gravity 13.6 compared to water, whose specific gravity is 1. You can see the adjoining figure where a gang mercury manometer has been displayed, and from the color itself you can see the silvery appearance of mercury in the manometer limbs. Why we are discussing about mercury manometer is because we are very soon going to discuss about the Rayleigh Pitot tube formula, and that is inherently connected with applications in supersonic wind tunnels. So, when we immerse a Pitot tube in a supersonic free stream, it acts as an obstruction, and therefore, it forms a shock wave, which is essentially a bow shock, but at the tip of the probe, this region happens to be nearly a normal shock. However, the same probe, when it is put in a low speed tunnel, as you can recall, it would not produce a shock wave, and it would see a much smoother flow pattern forming around the probe. Now, at the mouth of the Pitot tube, at the point E, that is marked here, the flow comes to a stagnation, and hence a fluid element moving along the streamline CDE is brought to rest at the point E. It is to be noted that the streamline CDE crosses the normal portion of the bow shock. Having said that, let us try to see what are the processes through which this streamline goes to reach the port tip ultimately. So, a fluid element moving along the streamline CDE is decelerated non-isentropically by the normal shock to a subsonic velocity at point D just behind the shock. Then between D to E, it is isentropically compressed to 0 velocity. So, there is a non-isentropic process here followed by an isentropic process over here. So, the pressure at the point E, which is basically being measured by the probe, is not the stagnation pressure of the free stream. This needs to be understood, but it is rather the stagnation pressure behind a normal shock. So, we can call it as P naught 2. You remember that this is the region 1, sorry, this is the region 1, this is the region 2 across the shock. Now, the pressure that is sensed by the Pitot tube is essentially P naught 2. Now, keeping in mind that you have a drop in entropy in the you have a drop in the stagnation pressure because of the increase in entropy across the shock. So, there is a loss in total pressure or stagnation pressure across the shock, and P naught 2 is less than P naught 1. Now, that is fine, but if you know P naught 2 and the free stream static pressure P 1, that will be substantial to calculate the Mach number M 1. Let us see how we do that. So, the next few steps are going to be important for us. So, this is the first equation we write. We are writing P naught 2 by P 1 as a ratio of P naught 2 by P 2 multiplied by P 2 by P 1, where P naught 2 by P 2 is the ratio of total pressure to static pressure in region 2 immediately behind the normal shock, and P 2 by P 1 is the static pressure across the normal shock. Now, from isentropic flow theory, you can express P naught 2 by P 2 as a function of M 2. Again, from normal shock wave theory, you can write an expression between M 2 and M 1. So, we are keeping track of these equations A, B, C. We will be invoking all these equations later. Further, the pressure jump across the normal shock can be obtained from an equation like this in terms of the upstream Mach number. Now, we will be basically combining all the 4 equations. Once you do that, you get an expression for P naught 2 by P 1, which is purely based on M 1, of course, assuming that gamma is constant, and for all practical purposes you can assume gamma to be 1.4 for air as the medium. This formula that you have now got is what is called as the Rayleigh Pitot tube formula. Now, if you imagine the experimental setup, so this is your Pitot tube from which you are going to get the P naught 2 more specifically. So, this is the shock wave. So, this gives you P naught 2, and if you have a wall port which measures P 1, which is in the region 1 ahead of the shock, then these two, if connected to two limbs of a mercury manometer, will help you to get the ratio P naught 2 by P 1. Once you get that ratio, this equation can be solved by hit and trial in order to obtain M 1. That means, using this measurement you can obtain the free stream Mach number. So, that is the Rayleigh Pitot tube formula. Next, let us discuss about possible methods of drag measurement. We will introduce the Pitot rake for performing wake survey behind a body, and then try to find out that how through that velocity survey in the wake of a body we can find out the drag acting on the body. So, you have a long metallic tube to which much more slender tubes are connected, forming an array of tubes which is often called as a Pitot rake. So, when this tube is immersed in the flow, then the tubes which are jutting out from the main thicker tube are going to act as individual Pitot probes, using which you will be able to estimate the velocities corresponding to each one of these stations. So, if you locate it in the wake of a body, then you should be able to get the velocity distribution in the wake of the body, assuming that the flow is approaching from the right towards the left. This is the idea behind a Pitot rake. So, let us try to discuss how, by measuring the velocity profile in the wake of a body, a two dimensional body more specifically, we are going to get an estimate of the drag acting on the body. For that, let us draw a diagram first. You have an airfoil here, and what we have drawn over here are some of the streamlines, and then using them we are going to draw a control volume. The control volume has to be drawn with care. So, you can notice that we have selected two streamlines, and just adjacent to that we are drawing a control volume. And then the control volume takes a turn here, it wraps the airfoil, goes back and joins here. What you have behind the body is a particular velocity distribution which you would be obtaining using your Pitot rake, or if you do not have a rake, even then it can be measured. You can have a single Pitot tube and then you need to traverse it in the wake by making it move this way to different locations, so that you can finally get this velocity profile. Let us call this profile as U2, and let us define the axis system like this. You have a free stream velocity approaching from left to right. This is uniform, much ahead of the airfoil. Let us name the different points on the control volume. This is A, B, C, D, E, F, G, H, I. So, that forms the control volume. These upper and lower streamlines are far away from the airfoil, that you can notice, and we are considering a domain which has a depth of unity, depth or span of unity. Since these free stream streamlines are far away from the body, we can say that the pressure is approximately equal to P infinity. Also, since those are streamlines, the flow cannot cross those lines. If you look at the body, on the body you have pressure and shear stress which is acting, and as a consequence there will be a resultant force. If you look at the wrapping part of the control volume, which comprises of D, E, F, that portion, then an equal but opposite reaction is experienced by the DEF. So, this is an equal but opposite reaction exerted by body on the control volume, specifically on DEF part of the control volume. Now, if we consider the surface forces acting on control volume, the pressure distribution and surface force on DEF, which is due to viscous stresses. We neglect the surface stresses on AB, HI. Why? Because they do not experience velocity gradients, and therefore, viscous stresses will not act on them. Then the next point is that any surface forces on CD and FG balance and cancel each other. Why? Because the CD and FG cuts are adjacent to each other and they are in opposite directions. Therefore, there will be a cancellation of the pressure and the stress effects. So, total surface force on entire control volume is essentially this, because there is no additional force to be accounted. The volumetric body force will be low because the density of the gas that you are dealing with is a low density gas. Let us call this entire force as F. Now, we recall the momentum equation this would be rho we are only concerned about the x component of the momentum equation, because we are interested in finding drag. So, we will end up using the x component only. Additionally, we will assume the flow to be steady. So, this term will go away. So, what are we going to be left with? We are going to be left with a form like this. This would be the form. Now, we take the x component of momentum equation, and if you do that, then this R essentially reduces to D, which is drag per unit span, because that is the x component of R, and what you are left with from the inertial part is this, and you are left with this. Now, if you look at this entire contour ABHI, we have taken it far away from the body, and therefore, for all practical purposes the pressure is more or less equal to P infinity everywhere, even in the upstream and the downstream stations. So, if we assume it to be constant all over, then when you integrate it over a closed contour, this is going to go to 0. Finally, what are we left with? We are left with this. Now, we need to look at how this expression further simplifies. If you look at A B, H I, D E, F, since these are streamlines, they would not contribute to V dot d s. So, V dot d s will be equal to 0 in those regions, and C D F G, they are adjacent and their contributions therefore cancel. So, only sections which would end up contributing are what? Are A I and B H, which are basically the upstream and downstream stations respectively. We have to account for the fluxes from those two regions. So, when we do that, let us try to write down the description for those two locations. For all practical purposes, we are talking about low speed flows. So, these are basically equal to rho infinity, and we are going to invoke the continuity equation additionally to the control volume. What will that boil down to? Again, remember that mass fluxes are going to again happen through these two sections only. All others are streamlines and therefore, they would not contribute. So, continuity equation gives you this. So, if I number this as 1, number this as 2, because these are the two important equations. So, what you do is you multiply equation 2 by u 1, which is essentially a constant, because that is the uniform velocity that we have upstream. What will we have? Rho 1 u 1 square dy is equal to rho 2, let us call this as rho only. So, what are we left with? We are left with rho u 2 u 1 dy. Let us call this as 3. So, if you substitute 3 in 1, then what do you get? You get rho u 2 u 1 dy plus rho u 2 square dy. So, finally, you will end up getting from which you should be able to non-dimensionalize and obtain C D. Now, this is uniform velocity, which can be obtained by doing a P naught minus P infinity using a stagnation and static pressures from a pitot static tube, and u 2 are going to be measured by your pitot rake or individual pitot tube with traversing arrangement. So, finally, once you are able to evaluate the u2 or rather obtain the u2 distribution, you just have to plug it into this integral expression, and these are the limits of the movement of the probe. The limits are essentially decided based on whether the change in u2 is occurring with traverse of the probe if it is a traversing arrangement, and if it is a rake, then you should be able to cover enough space so that all the variations in velocity are automatically captured. So, this is the basis of the drag measurement using velocity profile. We will quickly look at another technique of drag measurement, where we are going to do it on a cylinder and by using a direct weighing method using a mechanical balance. So, in order to make the understanding simpler, we will in the beginning itself try to draw a simple sketch which makes it clear to us what is the idea behind this method. So, we are going to have again a similar vertically oriented test section with a circular cylinder model. If you take a test section, if you take a cross section, then it will show you the circular cross section here, and then you have a fulcrum suitably located, and you have a weighing pan where weights can be put. So, based on this arrangement, let us try to see the discussion. So, it is vertically oriented and the model is suspended on a drag balance. So, we are calling this arrangement as a drag balance, which uses the direct weighing technique. That means, we are going to use some weights here in order to assess the drag which is acting on this body. As the flow moves past this cylindrical section, there will be pressure distribution, there will be skin friction, and as a consequence there will be a drag force which will be felt by the body, which will try to move it down. So, one part is its weight, the dead weight, which has to be initially balanced by some weights on the other side, the other pan as well. And then additionally, when the flow takes place, there is drag which has to be additionally balanced by some further weights put on the other side. Keep in mind that the distance between the CG of the cylinder and the fulcrum is the same as the distance between the fulcrum and the weight pan, and therefore, the moment of the forces about the fulcrums, they can be written as the force, the total force acting on the cylinder times this length is equal to the total force acting on the weight pan side into the same length, and therefore, it is equivalent to saying that the total force on the cylinder side is equal to the total force on the weight pan side. Let the cylinder diameter be d, length be L, all in meters, having consistent units. Now, before the wind tunnel is started, a weight equal to that of the dead weight of the cylinder, WC newtons, is placed on the drag balance weight pan to obtain initial balance. CG of model and the weighing pan are at equal distance from the fulcrum. After the wind tunnel is started, additional weight of W Newton is put in the drag balance weight pan, and the test section velocity is adjusted till perfect balance is achieved between W and the cylinder drag force. Based on whatever available weights are there, you may need to tune the u infinity suitably, so that you get perfect balance between the drag and the weights that you put on the other side, for which you need to have some throttling arrangement, so that the flow rate within the tunnel can be changed conveniently, almost continuously. The Pitot static tube placed in the test section, that means you will have to have a Pitot static tube placed suitably, let us say upstream of the body, is connected to two limbs of a manometer. The manometer reading is delta H meter. from the difference between stagnation and static pressure of the pitot-static tube, you should be able to gauge what free stream velocity is being produced. So, this is the manometer part of it and the pitot-static tube reading, from which you get the dynamic pressure basically, and from the weights that you have put, you can say that the weights that you have put equals the drag. This is only that incremental weight that balances the drag part only, it is not the dead weight part, and this of course includes pressure and skin friction drag. Once you put it into the formula and you non-dimensionalize, the weight which is the same as the drag comes on top. At the bottom you have dynamic pressure into the projected area, which is nothing but the d, the small d into the L, L being the small l, that is the length of the cylinder. A question to be asked here is that if you had made a pressure measurement on the cylinder and tried to estimate drag using that, would it be the same as this drag? Of course, the answer is that no, and it will be actually less than this drag, because this drag which you are measuring accounts for both pressure as well as skin friction effects, which a pressure measurement alone cannot reveal. So, in this lecture we started by discussing the Rayleigh Pitot tube. We also discussed about mercury manometers, which are going to be used in accompaniment along with the Rayleigh Pitot tube. Then we discussed about drag measurement using wake survey. This method utilized the concept of momentum deficit in the wake of a two-dimensional body, which equals its drag. Subsequently, drag estimation of a cylindrical body was discussed using direct weighing method. Thank you.